Hi, it's time for another math easy solution. Today I'm going to go over Leibniz rule, and just note in my earlier videos I was pronouncing his name Leibniz. And a lot of people give me feedback saying that's not how it is. Anyways, I'm pretty sure it's pronounced Leibniz rule. So Leibniz rule, and look at the generalization of the product rule for derivatives. So let's just jump right in. And as always, you could play this video at a faster speed and so on, and you can also download and read the notes or view the notes on a Hive blockchain or watch it in parts, and the links will be all in the description below as per usual. And also, let's just jump right in. So topics to cover, and this video is going to be a bit shorter than my usual multi-hour ones. But anyways, let's just jump right in. So part one, we're going to look at recap on the product rule for derivatives, then look at Leibniz rule, generalization of the power rule, or product rule, not power. Product rule for derivatives, and then look at proof of Leibniz rule, and then manually determining the nth derivative using the product rule. And then also look at the end synchronicity with the binomial theorem, which is quite fascinating stuff. So let's just jump right in. So recap on the product rule for derivatives. So recall from my earlier video in which I covered the product rule for derivatives. So here's a link to my earlier video, and then I just took a screenshot from my calculus book because it's a bit neater. So the product rule: if f and g are both differentiable, then d over dx of the derivative of f of x times g of x is equal to f of x times the derivative of g of x, and then plus g of x times the derivative of f of x. In other words, you just add these up. So the derivative of this product, you add these up, but you alternate which one you're taking derivative on each one. So the first one here, you'll have derivative of g of x, and the second one you'll have derivative of f of x, and then you just multiply this product like that. Note that we can write it in the following notation, or we can also write the product rule in the following equivalent notation, which is going to be, you could write it like this: fg, just for shorthand, and you could do a prime like that. This equals to, well, f prime g plus, and then you could just put it like this: f g prime. Just a bit easier to see than this one over here. Or you could also write it as or fg, that's the prime, that's the derivative, or you could write it as bracket 1 like that. This equals to f, and then the first derivative of f, and plus here f times the first derivative of 1. And then this one could write it as 0 for the 0th derivative, and so on. These are all equivalent. And this notation will be seen when we look at the generalization of the product rule. So now let's jump right ahead. So Leibniz rule, generalization of the product rule for derivatives. So the following generalization of the product rule. Yeah, initially I accidentally wrote product power rule for everything. The following generalization of the product rule is known as Leibniz rule, or general Leibniz rule, named after Gottfried Wilhelm Leibniz, and the proof is taken from Wikipedia. So here's Wikipedia. It's general Leibniz rule in calculus. The general Leibniz rule, named after Gottfried Wilhelm Leibniz, generalizes the product rule, which is also known as Leibniz rule. So yeah, that's interesting. So they call the product rule that, but other places they just label the Leibniz rule as the general one, and then this one as a product rule, and so on, or a specific case of it. But either or, I'll just use Leibniz rule, because that's what was being used by this other university that I was looking at, the proof for multiplication and division of a power series, which is another video that I'll be uploading shortly. So anyways, so it states that if f and g are n times differentiable functions, then the product f times g is also n times differentiable, and its nth derivative is given by, so you have that notation I showed earlier here. So we'll have f times g, then the nth derivative. This equals to the summation from k equals 0 to n of n choose k, that's binomial coefficient. And then this is times by f to the power of n minus k, n minus kth derivative, times it by the kth derivative, like that. So yes, fascinating stuff. So where you have this n choose k, and remember I discussed this in my earlier video. Briefly, it shows up in combinatorics and so on. This n k bracket, this is equal to n factorial divided by k factorial, and then times by n minus k factorial, all factorial there. And this is the binomial coefficient, and f to the power of j denotes the jth derivative of f, and in particular f to the 0 or f 0th derivative of f is equal to f. just normal function f like that. The rule can be proved by using the product rule and mathematical induction, and that's what I'll do in this video. So the proof is from this. I derived it from this Wikipedia page, but I'll expand on because they don't cover it in any depth. And yeah, note again the different derivative notation. So we have over here, yeah, this J1 like that. Basically, this all means the same thing. So you could write f to the jth derivative like that, and this equals to, let's put it like this, f to the j, and let's say we were dealing with x variables. The other one if we're doing this one, we're going to be assuming the variable depending on the context, but yeah, usually x like that. This equals to d over dx, derivative in terms of x. This is going to be the jth derivative. These are all equivalent notation. This is going to be f of x like that. Yeah, so going further, so thus we can write Leibniz rule in a more formal derivative notation as well as in an equivalent alternative form. You could write this, because you could just move these over. Instead of n minus k there, you could have a k over this one. Because remember, you could just flip these around. F times g is the same as g times f, and so on. So you could just switch those up, and the symmetry, yeah, it's all symmetric. As I'll go later, it was showing with the binomial theorem and Pascal's triangle. And again, it's pretty much identical. But instead of derivatives, you're looking at powers of a binomial, which I'll cover in a bit. So we could write this as, instead of this notation, let's write the formal one. So we could write it as d over dx. This is the nth derivative of, and then we'll write this as fx times this fx g of x. And we'll just, yeah, so we'll just leave it like that. You could put a bracket around it or just leave it like that. And this is going to be, assuming, yeah, signaling is for all of these. It's for both the product, or you could put this for completeness. So you could do either or, but a lot of places they just leave that out. And I'll just leave it too. Yeah, so this equals to the summation up to n from k equals to 0. And this is going to be f of n minus k. And then we'll write x like that. And then this times it by g to the k, like that, of x. And let's just scroll up here, so it's the same thing there. I'm going to use the more general one in the derivation, just because it's just be a bit more formal. It's because I've been dealing with that mostly. So this you can write this in the equivalent notation. Is going to be f of k, because you can just flip these around. F of x times g of x, same thing as g of x times f of x. So then you'll just switch these around. It's the same thing. F of x like that times by g, and then n minus k of x. So these are all equivalent. And yeah, I forgot to add the binomial coefficient. So let's just move this around and then write this down here. So n choose k, and this one's going to be n choose k, like that. Alright, so now let's jump further. So let's look at the proof of Leibniz rule. So the proof involves the principle of mathematical induction, referenced from my earlier video. So if you look at this right here from my earlier video and screenshot from my calculus book. So mathematical induction, in proving statements that involve a positive integer n, it is frequently helpful to use the following principle. So principle of mathematical induction. So let s sub n be a statement about the positive integer n, and suppose that s sub 1 is true, so part 1. So suppose that's true, and then suppose part 2, sk plus 1 is true whenever sk is true. So in other words, if we assume that s sub k is true, and then when we do that, we'll find out that sk plus 1 is always true, and that means, yeah, but starting from s sub 1 is true, then basically this means it's true for all positive integers right here. Then s sub n is true for all positive integers n, and this is reasonable because since s sub 1 is true, it follows from condition 2 with k equals 1. Yeah, so you just put k equals 1, that means s2 is true because we know s1 is true. So we just increment, so s2, then using condition 2 with k equals 2, we see that s sub 3 is true, and again using condition 2, this time with k equals 3. We have s sub 4 is true. This procedure can be followed indefinitely. So yes, keep going on and on, non-stop. So that means, yes, for all positive integers, this will be true. So we just use mathematical induction for that. So when n equals to 1, the Leibniz rule becomes just a product rule for derivatives. And we can see that. So let's just use this notation. Or we'll use this notation, but we'll use this one here, f to the n minus k, and then k like that. So let's just prove this using this notation, and we're going to have n equals to 1. So that means the n equals to 1. This is just going to be, well, d over dx. You could put a 1, you could put a 1, it's the same thing. And this is going to be f of x, g of x, like that. This equals 2, and then the summation from k equals to 0 up to n equals 1. N equals 1, like that. And then we're going to do, this is going to be 1, choose k, like that. And then write this out. This is going to be f of k minus, actually not k minus, 1 minus k, and that's again, let's just look at this one here. So yeah, 1 minus k, so n is equal to 1, and then this one's going to be just k. This can be of x, and then g 1, this is just gk, like that, of x. Now we can expand this fully out. Let's just expand this out, put k equals 0, the first term is going to be 1, 0, and then f to the power of, well, I mean f, this is going to be 1 minus 0, derivative, that's just going to be 1. And this is going to be of x. And the next one, this is just going to be g of 0, like that, of x. Then plus the next term is only going to be 2 terms of 1, 1. Yeah, so we have this 1, 1 like that. The next one's going to be, well, 1 minus 1 is going to be 0. So 0, and then this next one's going to be, this is of x, like that. This is going to be g. Now I'll just put this here, 1 minus 1, that just equals to 0. And then g of, is going to be 1. So 1k equals to 1 of x, like that. And now we can just expand these out using the factorial formula, and that is right here. This n choose k is equal to n factorial divided by k factorial times n minus k factorial. So let's do that. This equals to 1 factorial over 0 is the k, 1 minus 0 factorial. Then write this out. Yeah, f1 just can be, let's write it like this, f of x prime, yeah, so f of x prime, then g of x, and then this is going to be right here, is going to be 1 factorial over 1 factorial minus, then 1 minus 1 factorial, and this is going to be f of x, the 0 just goes away, and it's just going to be f prime of x, like that. And recall that this 0 factorial, this just equals to 1, and that equals just to 1 factorial, they're all the same thing. Yeah, so this is equal to 1, that means, well, this is going to be 1, this would just, well, this is going to be 1 divided by, well, this is going to be 1, and this one's going to be 1 minus 0 factorial, it's going to be, well, 1 factorial is equals to 1, so that all equals to 1, so this just becomes 1. So this just cancels with this, and everything cancels. And this one here too, this one's going to cancel with this, and this 1 minus 1 is 0, 0 factorial is just 1. So in other words, this just equals to 1. So this means that this equals to f prime of x times g of x plus f of x times g prime of x. This is just a product rule. Like that. I'll say product rule. So yes, exactly what we expected. So yeah, derivative of the f of x times g of x and plus f of x times the derivative of g of x. And let's just look at it right here. And yeah, it's right. We could just do it like this one. fg, and then we have the prime plus f prime times g plus f times g prime, like that. And yeah, for completeness, we could just put another one, or f of x, like this, g of x. Then you just put a bracket like that, prime. You do prime like that equals to f of x prime, and f prime of x times g plus, you could do f of x. Yeah, just fix that up. So yes, plus f of x times g prime of x with the including the x. So yeah, many ways of writing the derivative. Yeah, and here just pause the video and just move it over in the middle here to make it a bit neater there. And likewise, you could also do with the same thing with here. Just put a f of x in the side and g of x inside of all these, and so on. So yes, many different ways. So we have this f times g, and then prime. I mean, the derivative is equal to f prime times g of x plus yep, right here, plus f of x times g prime of x. So yes, many different ways like that. And you could also alternate which prime is first, and like this one, and so on. Anyways, let's keep going further. So that's the product rule. And yeah, so going further, so note that again here, note again that 0 factorial is defined as equal to 1, like that. And thus we know that Leibniz rule is true for n equals 1, i.e. it's just a product rule, in which I proved in my earlier video, so you could check out that video for the proof. So now let's assume, this is the key word there, it is true, or let's assume the Leibniz rule is true for a fixed nth derivative, just pick any random n, where n is greater than or equal to 1. Yeah, so if we assume it's true, well, we just get the form is going to be exactly as our Leibniz rule. So this can be d over dx to the power of n. This can be n like that, and we're going to be dealing with f of x, g of x, and you take the derivative, this equals 2. So we're going to assume that it's true for the just a random n variable, like that. This can be n up to k, starting from k equals 0, n choose k, and then this is going to be f of n minus k, x, then g, and this is going to be k of x. So we assume that it's true for this. Alright, so now that we have it like this, so now the next step in mathematical induction is to prove it is true for n plus 1, so the term after it, which we will do so using the product rule. So that's taking the derivative we have, so we're going to take a derivative of this scenario. So the next derivative of it's going to be, well, d over dx n, and then like this is going to be the power of n like that, and the next derivative after is going to be a plus 1, like that, of fx. Fx times g of x. And again, this is the same thing as writing d over dx of this entire derivative. So we're going to take the derivative of this entire thing, because we're going to assume that is true. So we're going to take the derivative of this entire summation, like that, and this is going to be n, k equals 0, n choose k, f of n minus k, of x, g of k. And let's just fix that up. So we got that sorted like that. So when we take the derivative of this entire thing, so we're just to note that we're taking the derivative because we're doing the n plus 1. So where we assume that this part is true, assuming the inside, and we're taking the derivative, and you're going to use product rule. Now this summation, what it's going to give us as well, it's going to be a sum of different products. So we could actually just take the derivative and split it up into two summations. So this equals to, using product rule, so I'll just put it down here, this equals to summation from k equals to 0 up to n. Yeah, so we'll take the derivative first of this f, and then I'm going to multiply by this g of x, and then do the same for the other part. So we'll do this one first. So that means, well, first we have our n choose k, this equals to f of n, and then we're going to have a, just put a plus 1 here. So just put that, and then we have the minus k like that. Just put it in front there. So that's the derivative of this one, the next derivative. Then just put our gk of x like that. And now we're going to add, because using the, we're going to add a full terms that we do the other terms for. And we do the other multiplication, or the derivative for. So from k equals 0 to n of n choose k, again using product rule. So now we just add this term, f n minus k of x, and then we take the derivative of all these terms. And again, summation just says we're going to be doing this many, many times. And then this can be k plus 1 of x. Like that. Alright, so now that we have this, what we want to do is we want to combine these together, but we have, these are different derivatives. This is going to be n plus 1 minus k, this one's going to be n minus k there, so we want these the same. So we want the same. Yeah, so we want these to be the same, as well as this k, and there's a k plus 1 there. So in other words, this is, yeah, this keeps jumping there. So in other words, this one is the k derivative, this is just one more than it, while this one is the derivative right after this one. Yeah, but what we can do, yes, we want these all to match up. So what we can do is replace, so here, replace k with k minus 1. This means that, so that this scenario, when we have k equals to 0, we get k minus 1 equals to 0. Move this around, so then we're going to be starting at k plus 1. At k equals to, k equals to 1 like that. And then at k minus 1, k minus 1 equals to n at this point. This would be k equals to, move this over, n plus 1. So all we're doing is just shifting how we're dealing with this. And now what happens to this part right here And also here, we could have just done set a different variable, but I'm just going to stick with k like that. And so that this was, this initial one is k equals 0, or just it starts from 0, goes to n. Now it's going to go from 1 and goes to n plus 1. And then here we replace all these k's with k minus 1. So that means here, n minus k, minus k minus 1. This equals to, well, this is going to be a plus 1 gets out of there, so we get a n plus 1 minus k. So that's going to be exactly the same as this part right here. And then likewise, the next part right here, k plus 1. So we have the k minus 1 is going to be replacing it with k minus 1 like that, plus 1. So the plus 1's cancel. We just get a k. So in other words, this becomes k, and then these would match up exactly. Yeah, so thus, again, we're just dealing with summations and manipulating the starting points and so on, and how they're going to interact. So this is going to equal to, well, this left side is going to be summation from, this is n, k equals to 0. This is where we start from, n, k, and also this part here is going to change to k minus 1. It's going to be like that. This is going to be f n plus 1 minus k of x. Whoops. Yeah, I don't know why my OneNote's always jumpy, but anyways, better than before. So this is g of k of x, and then plus, this is going to go to n plus 1, and now we're going to start at k equals to 1, so that's where we're starting from, or k minus 1 equals 0. So we're starting from there, and now this is going to go n, this is going to go n, this is going to be k minus 1, so we're replacing k with k minus 1. So yes, replacing it with this into every single one of them. We could even circle this. So this is going to change. So it's going to change to k minus 1 and so on. And then we're going to put a bracket like that. And now what we have is the next part is this part right here. That's going to be our n minus k, which is now going to be n plus 1 minus k. So that's going to be f of, this is going to be n plus 1 minus k. So again, matches up with this. So this matches up with this of x. And then the next one is g of, well, this is going to be k minus 1 plus 1. So just k. Like that, of x. Alright, so now we have this, and here we leave this n here by itself because that n is just part of the formula, whereas a summation, this is actually for more accuracy or just for more clarity. What this means is k goes to 1, this goes to k equals to n plus 1. And this just means from k equals 0 all the way up to k equals to n. So yes, that's why we switched it, but this n stays the same. So that's just n like that. But now what we have is, well, this starts from k equals to 0 and ends at k equals to n. This one goes from k equals 1 and ends at k equals n plus 1. So what we want is we want these the exact same, and then we could factor out these two derivatives. So this f of the n plus 1 minus k derivative of this f of x, and then the kth derivative of g of x that's equivalent on these two. So these ones we want to factor out, but we need these the equivalent. So what we're going to do is we're going to remove this k equals 0 part, and we're going to remove this k equals n plus 1 part, so that we're going to have from k equals to 1 to k equals to n. So in other words, we're going to remove it. This equals 2, and let's see how much space we have. So I'll just write this out as here, as from k equals to 1 up to n, and k f of n plus 1 minus k of x, g of x, g k of x. And then what we're going to do is, we're removing it, so I'm just going to put a plus here at the bottom. We're going to remove the first term, the 0th term, so n0, this is going to be f of, and then when you have k equals 0, that just becomes n plus 1 derivative of x. And then this is going to be g of k is 0, like that, of x. And then for this next term, so we're gonna get rid of the n plus 1 term. So let's underline this, and this one right here, underline that. So we're gonna get rid of that. So this is gonna be equal to plus n k equals to 1. Leave it at k equals 1. So from n k minus 1 And let's see if we can fit this all in. Alright, let's try that again. This is going to be f n plus 1. Just write it back down. Minus k. This would be of x. And then g k of x. Like that. So we got that. Let's see if it fits all into the page. So that's good. And yeah, so we got rid of the n plus 1 term. So that means we're going to have a plus. Just put it all down here. It doesn't fit. So we're going to have a plus n. This is going to be n plus 1. It's going to be n plus 1 minus 1. Because we have this minus 1 there. N plus 1 minus 1. Like that. So this just becomes, well, n over n. So I'll put it like that. This is just n plus 1 minus 1 equals to n like that. Yeah, so that's what it equals to. So we have n0 and we have n and my combinatorics or factorial hunch is tingling, and this says these should be equal. So n choose 0 and n choose n should be equal, and as I'll show, they in fact are, and they're equal to 1. So we'll do that soon. So this is going to be equal to, well, when you plug in n plus 1 inside here for k, so we have n plus 1 minus n plus 1, that equals to, yeah, this equals to 0. Like that, of x. This is going to be n plus 1 minus k, which is our n plus 1. Like that. So that just cancels out. And then the next one is going to be g of k, which is n plus 1 of x. And here's put a little line like this, a note, and just do some solving right here. Note. So we have n choose 0. This equals to n factorial over 0 factorial n minus 0 factorial. That's just our binomial coefficient. And this one we know is 1. So that's just equals to 1, 1, and then this n minus 0 is just n. These cancel. This just equals to 1. Yeah, so circle this, put a better one. Okay, so that equals to 1. And also n choose n. This equals to n factorial over, well, n factorial, n minus n. This cancels, this equals to 0, that equals to 1. So this equals to 1. Like that. Alright, so now that we have is, well, we have here, this k, this summation from k equals 1 to n. This one's from 1 to n. And then this entire summations are all equivalent, except the only difference is right here is this n choose k, this is n choose k minus 1. So we could factor those out or factor this out. All we're left with is an addition of these two. So let's just do this and bring this all down. This equals to, and also let's write this first one, let's write this term first. So this will be equal to, because we took it out of this left term, this one we took it out of the right term, so we'll add this last. And this is n choose 0. So this equals to f of, yeah, so this just equals to 1, so we get rid of that. F of n plus 1 of x, and then we have the g0 of x, or that just becomes g of x. Yeah, it's just for completeness, just leave it out of there, or just for convenience, leave it out of there. And then now we're going to factor out that big summation, combine that into 1, so this equals to from up to k equals to n, or just put an n for convention. So this starts from k equals to 1. So this starts from k equals to 1. We factor out this term right here, or these terms, the f and g derivatives. So factor that out, and then we're going to have this addition of these binomial coefficients. So this is going to be equal to, put a bracket, big one like that, n choose k plus n choose k minus 1, and then multiplied by the derivative f. And again, yeah, it just keeps jumping. I think I need to move the mouse there, click it here. Alright, let's just type this one in. So this is going to be f of n plus 1 minus k of x. So that should be it. And then the next one, k's derivative. G k derivative of x, like that. Let's see if we get it all on the same page. Yep. Alright, perfect stuff so far. And then the last term here, the one we took out of this one, so that's this one here. This n choose n is equal to 1. So we get, and this is a 0 derivative and then n plus 1. So basically the mirror image of this is going to be equal to, let's put a plus right here, plus f of, well, 0. G of, this is n plus 1 derivative of x. Like that. So yes, everything's just mirror images like that. And that's when there's mirror images, a likely binomial coefficient will arise. Alright, so now the next step is, well, let's simplify this part here. So we're going to simplify this, and choose k plus and choose k minus 1. And write this a bit better. Like that. Yeah, so now that we can, now you remove that. Yeah, so now we can simplify the binomial coefficients by expanding and adding together. So this one here, we can simplify it further, and then we'll get back to this formula. So let's do this right here. So nk plus n, and then k minus 1. Yeah, so this right here equals 2, and yeah, Wikipedia didn't prove this in their proof. It didn't derive this, and I was wondering what just happened. When you look at the proof, it's it just goes straight to the answer. So what this happens is you could expand these out as their binomial coefficients. This equals to n factorial times divided by k factorial, n minus k factorial plus n factorial over, yeah, so over. Now we're gonna get a k minus 1 factorial times it by n minus. Remember n minus k, this is going to be k minus 1 factorial like that. So that's what we have so far. Let's keep going further. Yeah, alright, so now that we've expanded this, notice what we can do. Well, this part right here, so this right here, this just becomes, let's put it like that. This becomes n minus, yeah, I don't know why my mouse, my whole screen keeps doing that. So this becomes n, let's try that one more time here. I'll try that one more time. So this becomes n minus k, and then there's, well, the plus 1 gets in the front. So this becomes n plus 1, and then minus k. Like that. Factorial. So that's what this equals to. Yeah, so this equals to that. But this right here, we can simplify this further because we want to, remember, we want to write it in this form. Yeah, we want it to look exactly like this, so we wanted the n minus k, but this is going to be just n minus k plus an extra 1. So in other words, we could just use our factorial knowledge. This equals to, yeah, this goes down further, this becomes n plus 1. We just take that entire thing out. Like that. And then times it by n factorial, n minus k factorial. Yeah, let's keep putting an equal sign like that. That equals to that. And yeah, keep going further. Yeah, so that equals that. So we have it like this. But now over here we have a k minus 1. So instead of a plus 1, we have a minus 1. So what we could do is we could just multiply top and bottom. So I'm just doing this all at one go. Top and bottom by k over k. So that this, now this part equals to, this is just going to be k factorial. That's all it is. Remember, factorials are just going to be k, then k times, k, then times it by k minus 1, times it by k minus 2, etc. Or, yeah, that's what the definition of factorials is. So now we just add a new one there, so it's going to be k factorial. So that's what this part equals to. Let's put it closer by here. Equals to k factorial there, just to make it away from this other equal sign. And leave this out of there. Yeah, so that equals to that. This equals to over here. So now this matches to this k factorial right there. So this matches, and now we have this matching with this one. So this all equals to, put it down here, equals to n factorial over k factorial n minus k factorial plus, and let's just write that down, k times n factorial over, this is going to be k factorial n minus k, or just move that k out of there, move it over here, so it's going to be n minus k factorial, and then this is going to be, put this, erase this dot. So we'll leave the terms that aren't factorials out, so that's going to be n plus 1 minus k, and there's going to be a k on top. So this can be times it by k over n plus 1 minus k. Just put a bracket. So that's not a factorial. Those are. So we will just factor out this entire thing. So factor it out. We get n factorial over k factorial n minus k factorial times it by, well, we factored it out. This just becomes 1 plus k. Let's move the 1 all the way across. Here's, yeah, this becomes 1 plus here k over n plus 1 minus k. And the reason put it over here, again, you just multiply top and bottom by n plus 1 minus k. N plus 1 minus k is get the same common denominator, n plus 1 minus k. Yeah, so just multiply that top and bottom, and now what we have is we could just multiply this 1 inside. Well, 1 is just going to be exactly this, and then sum all these up. So we get, and when we sum those up, we get n factorial over k factorial n minus k factorial, and let's make this a bit better. Like that. This becomes times it by, so n plus 1 minus k, this minus k, this k cancels. This cancels with this. So what we get is, we'll draw this better, cancel like that, and draw this bit one more time. K, yeah, so, alright, yeah, drew that a bit better. Yeah, so that's going to be, at the top it's going to be just n plus 1. Then at the bottom we're going to have, well, it's just going to be the same common denominator, so n plus 1, n plus 1 minus k. Like that. And now this one right here is just one more of this n minus k. So in other words, this combines into a factorial. So this right here combines into a factorial. Actually, here I just moved it down here. So now this is one more of this one. So that means we could write this whole thing as a n plus 1 minus k factorial. And likewise on the top is n factorial and this n plus 1. This is just one more of this one. That means when you multiply it together, this becomes n plus 1 factorial. So yeah, this is pretty amazing stuff. So n plus 1 factorial over this right here. So this equals to, and let's just put it down here, this equals to n plus 1 factorial over k factorial, and then times it by n plus 1 minus k factorial. In other words, this n plus 1 is replace our new n. So this equals to n plus 1 over k factorial. I mean, not factorial, n plus 1 over k, or n plus 1 choose k in our binomial coefficient, and this deserves a hashtag. We'll put a circle like this. This is pretty amazing. Hashtag amazing. So hashtag amazing stuff. So yes, fascinating. Yeah, so now that we've got this done, so thus we can continue simplifying our derivatives. So let's just scroll up to where we started or ended off at. So we ended off over here before we simplified this one over here. And this one's just going to become now n plus 1. And then this is going to be choose k, like that. So that's what it's going to be. Yeah, so we can write this exact same thing, and then we're just going to simplify this to n plus 1 choose k, or bracket k, like that. And yeah, this whole thing is, again, it's just the derivative after the nth one, so n plus 1 derivative. So let's just write that down. So we're going to have d over dx, this is to the n plus 1, yeah, plus 1 derivative of our f of x times g of x product. And now this is going to equal 2, so let's write the first term of this one, fn plus 1, then the last term goes, alternates, the derivative for the g is the n plus 1. So it goes to fn plus 1 of x, g of x, and then let's just put the next one over here, f of x, g n plus 1 of x. And then let's add our big giant summation. That's this summation over here. Summation from k equals 1 to n, and this is going to be this. This is n plus 1 minus k. This is just k. So let's just write this whole thing down. This is going to be from k equals to 1 up to n. Now it's going to be our simplified n plus 1 k, and then it's going to be our f of x. Our f of x n plus 1. Yeah, n plus 1 minus k fx, and then this is a g of kth derivative of x, like that. Yeah, so just move it over there, and also I'm going to move this over. I'm going to shift it over to the right. Let's just highlight this one more time. Okay, so we move this over to here. And the reason I'm doing that is because, well, for these two, this one right here, notice that it's n plus 1. And then this one is a derivative here, just a 0. This one is n plus 1 minus k, and then goes to k over there. And then this one has the just a derivative. This is a k0 here, and then this one is n plus 1 yeah, just, this one becomes n plus 1 then. Or this one, this is the 0th derivative, this is the n plus 1 derivative. In other words, what we have on these ones, this right here, I'll put it over here. So this, whoops, make an arrow like this. This is equal to, this one's going to be, well, in the front here, this is n plus 1, and then it goes to, yeah, it goes to this n plus 1, this one is going to be 0 here. In other words, if you look at the series on this one here, or the summation, I mean, so we have n plus 1k. If we let k equals to 0 there, this becomes 0, so it becomes n plus 1. This becomes 0 there. So in other words, this right here is going to be n plus 1 choose k, because, well, we know this is equal to 1. N plus 1 choose k where it's 0. And where this one here, we know it's equal to 1. Because if we scroll back up all the way up to our earlier here, so n choose 0 is going to be, well, these cancel, is equals to 1. And if this was equal to n plus 1, nothing will change. This will just be n plus 1, this will be n plus 1 factorial, they cancel, go to 0. And likewise, if this is n plus 1, and this is also n plus 1, these would cancel, and then these would just subtract to 0, and factorial is 1. So in other words, we already know that equals to 1, so we can just write that in front, and then write this as just our usual n plus 1 x g of x, like that. And then while this part right here, because remember, now this notation matches this exactly. Now we could actually just combine them all into that same series. So this part right here, now this part right here, we know that this is equal to, let's put another arrow like this. This is equal to, and if you look at this one here, so if we put n plus 1 inside here, n plus 1 inside k, so this is where k is equal to 0. And this one's going to be, I'll put a k like around this arrow, k equals to n plus 1. Because if we put k equals n plus 1 inside here, n plus 1 minus n plus 1 goes to 0. And then we're going to have here first n plus 1 choose n plus 1, which is, we know this is equal to 1. Equals to 1. And then we're going to have our f of n plus 1 minus n plus 1, that's a 0. So this is just going to be f of x like that. Or for completeness, let's just put the 0 inside there. And then this is going to be g of n plus 1. Yeah, so k is n plus 1. So it's just n plus 1, like that, of x. Yeah, so for completeness, we could also write this as, remember, this is just our n plus 1 minus our n plus 1, where k is equal to n plus 1. And they just cancel, goes to 0. This one is just k equals n plus 1. Yeah, this part is just k equals n plus 1. This one here is just this part here. And we add a k is n plus 1. And also let's do that for this case here. This is when we plug in 0 inside here, n plus 1 minus k is 0. This is just our n plus 1 minus 0. That's our k. So it just becomes n plus 1. And then this g is just where k is 0, so just put a 0 like that, just for completeness. So that it matches exactly this. So this is exactly this formula. And in other words, we can combine these all into the series. So thus, yeah, so put these right here. Thus, so let's put the whole entire derivative down. So we have d, this is n plus 1 derivative of dx n plus 1, just a notation like that for the n plus 1 derivative of f of x, g of x product is equal to the summation. And now this is where k equals 0. This is where k equals n plus 1. So in other words, we're just going to expand this series. So start off from k equals to 0 up to n plus 1. Up to k equals n plus 1. And this is going to be n plus 1 k. Then now we have over here, we just write down this whole thing. So this entire derivative is equal to f of n plus 1 minus k of x, g of k of x. And I'm just going to box this out. This just proves our mathematical induction. This is exactly the Leibniz rule for the n plus 1. So basically, using the product rule for assuming the derivative of the nth derivative is true for the Leibniz rule, we showed that this is true for the n plus 1 derivative. Because here we just added one more, and notice here, this is exactly the formula. We just replace n with n plus 1. So n becomes n plus 1, this becomes n plus 1. And let's just scroll back up to the official formula. Yeah, so the official formula is just this n minus k, and then k. Now all we did was replace n with n plus 1. So when we replace n with n plus 1, and any of this becomes true. So we know that it's true whenever the n is true. Yeah, so this is the result if we had just used the Leibniz rule. Just write it down here. And replaced n with n plus 1. So if we just replace n with n plus 1 in the Leibniz rule, we get this. In other words, we just proved it for all n then. Thus, our mathematical induction is complete, and Leibniz rule is true for all derivatives or for all n is greater than or equal to 1. So let's continue further. So now we've proved it. Now I'm going to just do this manually just because it's a pretty good exercise. So manually determining the nth derivative using the product rule. So we can see the pattern that arises when we manually derive the consecutive derivatives of the product of functions f and g. Note that I'll be using the short form derivative notation just because it's quicker and to compare with the faster one above, or with the more formal one earlier that I just proved the product. I'm going to prove the Leibniz rule. So if we have fg and then take the derivative, which is the first derivative, it is just going to be f prime and then g plus f g prime. So you just alternate the derivatives and add them. So f prime times g, then f times g prime, or the derivative of g. And now we do the next one. Now take the second derivative. The second derivative is going to be, well, derivatives of these ones here. So it's going to be f double prime, then times g, and then plus f prime times g prime. And now this part right here, we take the derivative. The first one's going to be f prime, then g prime. And now notice these ones add up. These ones line up, so you can add these up. And then the next one of this is going to be, well, f and then g double prime. Notice the symmetry. So it goes f double prime, and then times g, then plus f prime. Then it's gonna be 1, 1. It's gonna be 2, 0, 1, 1, 1, 1, and then it's gonna be 0, 1, 1. So it's perfectly symmetric. So I'll do that here. Yeah, these add up. But also this one right here, I'll just do this like this, or actually put a line here for adding up. And now here, there's a perfect symmetry. Yeah, perfect symmetry. You're going to see this further. Yeah, we're going to see this further. So these add up. So this is going to equal to f double prime of g plus, and now we're going to have a 2. 2 f of g. So it's going to combine exactly at the symmetric points there, and plus f. This is going to be f prime prime. This is going to be g prime prime. And this is going to be f, g double prime, like that. So yeah, that's going to be like that. And now let's take the derivative again. So the third derivative, f g triple prime. So we start off where we ended up here. Now let's take the derivative here. Notice symmetry could be third derivative of the g, zero derivative of the, third derivative of f, zero derivative of g. The next one here we have these with the coefficient 2, the binomial coefficient, which you can just calculate it with it. And now it's going to be equal to, this is going to be 2 f double prime. So we just subtract the derivative here. This is 3. This is going to go to 2. Now it's going to go to g1, then plus 2. And now it's the exact mirror image. So this is the halfway point. So now we mirror image it, and this is going to be f like that, f prime, then f double prime there. So mirror. It's like mirror or reflection, or however you want to call it. Yeah, so the next one's going to be, well, it's this part right here. And in fact, we forgot to take the product rule expanded to this one. So let's just expand this, or move this over. We forgot to do it on there, because again, you can all see with the symmetry, and that it should be it. So this one here is f triple prime and then g. Then you have to do, finish the product rule on this one. It's going to be g prime, like that, and then plus. So there's a perfect symmetry over there. And let's just move it a bit closer so that we can fit it all in. And then the next one's going to be, well, symmetric with this one. It's going to be f prime g double prime, or just look at it over here. Take the derivative f prime g double prime, and then the derivative goes to f and then g triple prime, like that. So there it is, perfect symmetry like that. So notice that the symmetric points always add up. Yeah, or better yet, the specific point of its mirror, the mirror symmetry, or basically where they pair up. So this right here, it's actually it's gonna pair up, but on its own side. So this right here, or even depends on what the scenario. So this one right here, 2f double prime and then g prime. This is over here. This matches it up with this one. So f double prime. So this is gonna be summing up, and then the mirror of the summing up is gonna sum up. Yeah, that's a better way to see it. So this 2f prime g double prime has its equivalent mirror with this one here, f prime g double prime. So we have second derivative and first derivative, and these match up, and then the exactly mirror image have to have a matching up. So this would be equal to f triple prime g plus, this is going to be 3 f double prime g prime, and then plus over there has exact mirror image plus 3 f prime g double prime. The difference, so yeah, with this one here, this is its own mirror image. This one has a mirror image split across here because it's an even number. That's an odd number. This is an even number. So yes, that's what I was looking at. Now it's going to be f, and the next one is, yeah, g triple prime. So it matches up with this. So there's the mirror. Let's do a mirror like that. Yes, let's draw it like that. Mirror, that means mirror. And this one mirrors, because it's odd, there's three terms. This one's 4 terms. So there's mirror directly in between that. It's just fascinating stuff, guys. Yes, all this mirror imaging, I learned this from that Vortex math video. If you check it out on MES Science too, it's pretty epic stuff. And now let's do one more derivative. Let's look at the fourth derivative. So the fourth one is going to be, well, you could write it as many ways. So you could write it like this: fg 4. Or you could write it as, just because we have this in this kind of Roman numeral formation, let's keep writing it like that. Or you could write it as fg in Roman numerals IV, like that. Yeah, so IV is 4. So let's just do it that way, and then we'll convert it all into this one right here. So this is going to equal to, let's take the derivative of this. This is going to be the fourth derivative, FIV of g, like that. Then times it by g, where g is just the 0th one, and then this is going to be, got to finish our product rules. It's going to be g prime. The next one's going to be over here, 3 f triple prime, then g prime, plus 3 f double prime, g double prime, like that. And since this is going to be the mirror image, so we stopped at the mirror image over here, and then the next one, let's just keep going over here. Let's just go around this way, so it's all lining up with its mirrors. Plus, yeah, so just going backward this way, just continue this because there's not enough room horizontally. But anyways, the next one's gonna be over here, 3f, then it's gonna be double prime, 3f double prime, and then g double prime, plus, yeah, so just working backwards. So now the next one's gonna be f prime, and then g double prime. I mean triple prime. So this was over here. This was gotten from here. 3 f is gonna be double prime, and g double prime, and then I'm trying to wrap my brain around. The next one's gonna be 3 f prime, and then g triple prime. Yeah, so it has to mirror this one. So notice the mirror. This is f is the third derivative, and this g is first. This one is reverse. F is 1, and then the g is the third derivative. And yeah, actually, this notation, you could write it this bracket, or you could just put it just IV or I, like that. Just put it like that. Actually, we'll just keep it like that. Yeah, so I've always written the fourth derivative and beyond like this, even though the 1 to 3, I just wrote it like that. So yes, it's many different notations. So the next one's going to be, the next one's over this one here. So this one is going to be the first derivative, and then this is going to be the third derivative. So it's going to be f prime. Yeah, f prime, g triple prime. And you could always double check with the mirror. So it has to be a mirror like that. And this is also, I'll put a, put a line like this. So this is also mirror. I put a tiny line like that. This is going to be mirror or dashed line. So it doesn't get over there. This is going to be our mirror. Or just put a solid line, but a bit thinner. So that's our mirror, but this wraps around over to here, and then plus, then the last one is over here, finish the product rule. It's going to be f, and then g fourth derivative, or quadruple prime. This is going to be f, and then g v. Notice perfect symmetry over here. Alright, so now we're going to have a symmetry. These two line up, so this and this line up, and then also, yes, these ones going to be adding up. So that's going to be 6f double prime g double prime. And then this one here is going to line up with this right here. So that one lines up together. Let's put it like that. This one I'll put an arrow like that. So that's because it's a part of the mirror there. It's going to be even number. And the mirror is in between those two. And then the next one here, f prime and g triple prime. So this is going to sum up together. So this equals 2. And now let's write this in the more formal notation, or just with this this notation over there. This is going to be equal to f. The first one's going to be f. Let's write it like this, 4. So this one's just going to be g. Then there's going to be plus f. This is going to be 4 of these, so plus 4. 4. And then this is going to be f3 g1. Yeah, those add up. 3g1. This one's going to add up together, so that's going to be 6. This is going to be 2g2. Now these add up. That's going to be 4. Exactly mirror image. The mirror is going to be across from here to there. Yeah, so we're going from even number here is going to go. It's going to go down to odd, because that should be the mirror right where these two were. This is going to be, now these add up is going to be 4, and then the opposite of this one, 4f1 g3. And then the next one is fg4 plus f g to the 4. Now, in fact, all these coefficients, they're all can be solved using the binomial coefficient theorem, the one with the factorials. And yes, I'm just going to continue dot, dot, dot. So I will not derive it for each one, and maybe in a future video I'll derive it. But let's go over here. So now we have fg. Now we just put this in general. So in general, it's going to be f to the power of n. This equals 2. Notice how all the patterns are exactly lining up. So it's 4, 0, 3, 1, and these are all the binomial coefficients. I'm going to write this as n choose 0 is the first one. We know that's going to be 1. It's going to be f of 4. No, it's f of n. Remember, that's 4. That's 4. This is 3. That's 3. So it just lines up like that. It's going to be g of 0. The next one's going to be n choose 1 f, and this is going to be 3 is going to be, well, n minus 1. Yeah, it's going to be n minus 1, and then g is going to be, well, just 1. Like that. So you're all subtracting whatever this one is. And it's going to continue going, dot, 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 or let's just do one more. It's going to be n2, and then f of n minus 2. G is going to be the second one. So notice here 3, 1, then subtract 1 and increase 1 on the other one. It's going to be 2, 2, and so on. Then it goes to 1. This goes bigger all the way. Yeah, or better yet, let's just try to fit it all into one horizontal line. So what I'm going to do is put this over here, and just put a plus dot, dot, dot. So let's put this over here. Yeah, just move it over, plus dot, 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 and then plus, and then just make this a generic k. Just fit it all in one. This is going to be k, this is going to be k. This is just our Leibniz rule there. Yeah, but the totals is you sum it all up. Now it's going to go plus dot, 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 plus, and then all the way when k is equal to n. And then when k is equal to n, we have n minus n is 0. So we're going to have f of the 0th derivative, and then g is going to be n. So remember, yeah, this goes to 0, and this goes to the 4th derivative, and then this goes to the nth derivative like that. Yeah, here I just shrunk it all to fit into this, and now this one is just a summation. Yeah, so now we get our Leibniz rule. And again, we're just assuming these are all the same coefficients, which in fact they are. Well, I might prove that for a future video. But anyways, we're gonna get a n choose k. This is k equals to 0, starts from 0 all the way up to n, and this is going to be our Leibniz rule, and that's gonna be this generic one there. And k, this would be n minus k, and then g k, like that. And let's just box this out. So there's our formula. And yeah, all we did was just assume these coefficients are in fact these n choose k binomial coefficients. Yeah, so yes, so to sum it up, this pattern, yeah, the pattern extends as expected based on the Leibniz rule, or based on Leibniz rule, like that. Yeah, Leibniz's rule. Yeah, so yeah, you can just sum it up consecutively and see the pattern, and it's just you're gonna form a Pascal's triangle with all these coefficients, and I'll get to that in a bit. So synchronicity or synchronicity with the binomial theorem. The Leibniz rule is almost identical in appearance with the binomial theorem, and the binomial theorem involves the nth power of a binomial, which is just the sum of two binomials or single-termed polynomials. For example, x plus y is a binomial because you're just adding two monomials, which are x and y. Which is just one term, x or y. You could also have x squared, y squared, etc. So while Leibniz rule involves the nth derivative of a product of two functions. So we get to the binomial theorem soon. So binomial theorem is just the nth power of a binomial, while Leibniz rule is the nth derivative of a product of two functions. And the binomial coefficients, or Leibniz rule coefficients, you can view them as that, can be determined easily by using Pascal's triangle as explained in my earlier video. So here's from an earlier video, which here it is. My earlier video on infinite sequences and series representation of functions as power series. And then in that I referenced Wikipedia as well. So we have binomial theorem. So in elementary algebra, the binomial theorem or binomial expansion describes the algebraic expansion of powers of a binomial. According to the theorem, it is possible to expand the polynomial x plus y to the power of n into a sum involving terms of the form a, so as the coefficient, a x to the power of b times y to the power of c, where exponents b and c are non-negative integers. With their addition, they add up to equals to n, with b plus c equals to n. In fact, even ours is the same here. So n plus 0 is n minus 1 plus 1 is going to be n minus k plus k is equal to n, 0 plus n is equal to n. In other words, here, 1 plus 3 is 4, n plus 2 plus 2 is 4, they always equal to 4. Let's keep going further. Yeah, and the coefficient a of each term is a specific positive integer depending on n and b. For example, for n equals to 4, we have x plus y to the power 4 equals to x4, and then y power of 0, plus 4x3 plus y power of 1 plus 6x squared y squared plus 4x y cubed and plus 4y4. I mean just plus 4 to the plus y to the power 4, and there's no 4 coefficient there. And it's exactly the same as ours here. We have here this would be 4 to the power of, fourth derivative there of f, and then g is going to be the 0th derivative, whereas this one here is the y to the power of 0 is equal to 1. They just removed that there. And then, yeah, so we have then it goes 4, there's a 3, 1, 6, 2, 2, 4, 1, 3, and there's a 0, 4. Let's go back to here. So yeah, there's going to be the 1, there's going to be a 1, this will be 4, another one 0, then we have a 4, 6, 4. And again, there's the same coefficients, same powers are 2, 2. And yeah, so we have 2, 2, 6, 4, 6, 4. Exactly the same thing we had. The coefficient a in the term of a times x power of b times y to the power of b is known as a binomial coefficient, where you have n b or n c. The two have the same value. So just going in reverse is the same thing. Yeah, in other words, yeah, see these powers right there. So yeah, so if you have n choose 0 is the same as n choose n, which I showed earlier. But it's also the same for n choose k. Let's scroll back up where we had. Yeah, scroll up here. Actually, I didn't prove it for n choose k, but you could just replace 0 with k, and you're going to get the exact same thing. As if we had n choose n minus k. Because you're going to have here, if this is n, this would be k. Yeah, if that's k, then you're going to have an n minus k, and likewise, if it's n minus k, you're going to have n minus k on this side, and this one's going to be n minus k. The n's cancel, you just have k. So all you do is alternate. Yes, exactly the same thing. Let's just scroll up here. Yeah, so the two have the same value because remember b plus c equals to n, so we can just do that right here. So n choose, for example, n choose b is equal to, this is right this here, n factorial over b factorial. Now we're going to have a n minus b factorial. But then c is equal to, over here, c, they add up to n, so c is equal to n minus b. So then this would equal to, put it right here, this is going to be n factorial, or actually this equals to n choose c, which equals to n choose n minus b, which equals to n factorial over, let's just prove it quickly. That's pretty interesting. This is going to be n minus b factorial. That's going to be our new b or new k. Now it's going to be equal to n minus n. This is getting n minus b factorial. These n's cancel. So what we're left with is the b. Just put it like that. This equals to b factorial, which are exactly the same. All we do is we rearrange which ones first. So, and then this one right here, put it above here. N, choose, so this is going to be n minus b. The n's cancel, like that. And we're left with just a plus b, like that. So yeah, just put it over there, and yes, fascinating stuff. Alright, here I just moved it around just to make it easier when I add these to the Hive blockchain when I add the notes. But anyways, move some space over to this. So these are equal, the same thing. So the two have the same value. These coefficients for varying n and b can be rearranged to form Pascal's triangle. These numbers also arise in combinatorics or probability theory, where n choose b or nb gives the number of different combinations of b elements that can be chosen from an n element set. So that's very interesting stuff. So basically, how many times b elements or b can be picked out of a how many b marbles can be picked out of a total of n marbles, and so on. So fascinating stuff. Yeah. So therefore, n choose b is often pronounced as n choose b, which I've been saying it nonstop. So anyways, let's go over here. So here's the Pascal's triangle. So we have 1. That's the coefficient of the first one. It's just going to be fg, and then this one's going to be 1 plus 1. So yeah, coefficients over there. Then the fourth one, 1, 4, 6, 4 is over here. So 1, 4, 6, 4, and then we have the notice the triangle 1, 2, 1. And then 1, 2, 1 is the one we had above here. So the first one is just FG, is just 1. Then it splits into 1, 1. Then it goes into 1, 2, 1. Then it goes into 1, 3, 3, 1. And actually no, these it goes 1, 3, 3, 1. Let's see if we have that correct. Yeah, so 1, 3, 3, 1. Then it goes 1, 4, 6, 4. And if we keep taking the derivative, the fifth one's going to have a 1, 5, 10, 10, 5, 1. And the binomial coefficient n choose k appears as the bth entry in the nth row. Yeah, where you have Pascal's triangle, counting starts at 0. So the bth entry, that's going to be the b here. In our case, it's k. So that's counting to the right. Then the n is the row. So this is n0, this is n1. This is the second derivative, third derivative. Is it fourth derivative, or fourth power for the binomial coefficients, for binomial theorem. So it appears, and each entry is the sum of the two above it. So we could have just added the above. So 1 plus 1, or this one here 1, the one above it is going to be 1, 1. Then when you add up the one above this, the two above it, so this 2 has 2 of these. So 1 plus 1, it goes to 2. Okay, 1 plus 1 goes to 2, and then this one here, 1 plus 2 goes to 3. And yeah, so on. So the sides are always 1 because there's nothing. You're just adding 1 above it. There's no other number. It's gonna be besides 0. This one here, 2 plus 2 goes to 3. Here, 3 plus 1, it goes to 4. This one here, 6 plus 4 goes to 10. So yes, that's Pascal's triangle. You could calculate them very easily. So yes, fascinating stuff. And then here's the formula for the n choose k is equal to n factorial divided by k factorial times n minus k factorial. I might prove this in a future video, in a future recent video, just get it out of the way. And now here, if you sum it up for just the general power, so x plus y to the power of n equals to n choose 0, x to the power of n, then we have a y to the power of 0, then we have n choose 1, x to the n minus 1, and then y to the power of y. It's exactly the same thing as we had. Then it goes all the way down over, so it just keeps going on and on. So n choose 2, this is going to be n choose n minus 1, and then x1 and n minus 1. So notice the mirror image across from here to here. So this is going to be a mirror image somewhere across there, and everything is going to be reflecting back until we have x to the power of 0, y to the power of n. This one's x to the power of n, y to the power of 0. So it flips, and this one's n choose 0, this is n choose n, where the mirror coefficients are the same too. And likewise here, even this with our case where we had a switch. So x plus y to the power of n is equal to summation from k equals 0 to n choose k is x to the power of n minus k, y to the power of k. It's the same thing as here. As you just flip these around, x to the power of k, y to the power of n minus k. Because again, you can just flip these around, nothing will change, and you could just, then you'll have it differently on these powers. So yes, MES, note the symmetry in the formula and terms. So in comparison, we have Yeah, we have, let's just write down this one here. So let's write down the power, the binomial theorem, or the powers of this binomial. This equals to, let's just write these down. N, choose k equals 0. This is n, choose k. X to the n minus k. And this is y to the k. And this is exactly our formula. And then for the derivative, we have, let's just write it in short form, fg to the power of, or the nth derivative of the product fg. This equals to, like that. This goes to n, this goes to k equals to 0, and then goes again, n choose k, exactly the same thing. Now we have the f is going to be n choose n minus k derivative. And then we have our g, which is going to be, instead of y, we have g. Yeah, g, k, like that. And again, this equals to, you could use the mirror image of it, or this the exact same thing. Yeah, the mirror image of it, it ends up just going backwards. It's exactly the same thing. So n, k equals 0, we have n, k, and then this is going to be x to the k, or y to the n minus k. Because again, it's just going backwards. Because here we have x to the n, and then it goes all the way to x to 0. This one we have y to the 0 always goes all the way back to the y to the n, or it goes in reverse. You can go start from here and go to the left. So y to the n goes all the way back to y to 0, and then x0 increases. So you could change which one's increasing or decreasing, but all it's stating is which one starts from the left or the right. So then the next one here is exactly the same thing. It's power of k. And this is going to be n, k equals 0, n choose k, and we have our f of k, g, and this is going to be n minus k derivative. Let's see if it all fits. So yes, everything fits fine. Let's just box this whole thing out. And yes, pretty amazing synchronicity. And this deserves a hashtag amazing. Like that. So yes, that is all for today. Hopefully you followed along, and yeah. So I just wanted to get the proof out of the way, and then I'll then basically just show the how far we can extend this, and just see some patterns, and do the manual derivatives, see the binomial coefficients arise, and yeah, I think it's about time I should prove that this formula, this n choose k, but it's pretty straightforward. Anyways, that is all for today. Hopefully you follow along, and yeah, and hopefully you enjoyed. And like always, you could download these exact notes in the link below, as well as watching these or reading these notes in article format in the link in the description below on the Hive blockchain. Anyways, that's all for today. Thanks for watching, and stay tuned for another Math Easy solution.